Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're moving into an important topic in acid-base chemistry. That topic being weak acids and weak bases. Last time, we talked about strong acids and bases, which we treat as being 100% ionized in water. For example, if you have 0.1 molar hydrochloric acid, then the concentration of hydrogen ions is simply 0.1 molar because every single molecule dissociates. The same logic applies to a strong base like sodium hydroxide, where the hydroxide concentration equals the initial concentration you started with. From there, we could calculate pH or pOH directly. Now, in this lecture, we're going to level up and we're going to discuss weak acids and bases. Weak acids and bases do not fully dissociate in water. Instead, they establish an equilibrium where only a fraction of the molecules donate or accept protons. That's why we describe weak acids and bases in terms of equilibrium constants, Ka and Kb. Now, the definition of an equilibrium constant, whether it be Ka, Kb, Kw, just K in general, it follows the same definition. It's going to be the concentration of your products raised to their stoichiometric coefficients and multiplied together, divided by the concentration of your reactants raised to their stoichiometric coefficients and multiplied together. And we do not include solids or liquids. So keep that in mind as we set up Ka and Kb expressions for the example reactions we cover. Let's start with weak acids. If we write a generic weak acid as Ha, it reacts with water to form hydronium ions, H3O+, and the conjugate base, A with a -1 charge. But unlike strong acids, the reaction, it doesn't go to completion. Instead, it reaches equilibrium, and we define the acid dissociation constant Ka to capture that balance. Ka is going to equal the concentration of hydronium ions raised to 1, because that's the stoichiometric coefficient, times the concentration of the conjugate base, also raised to the power 1, and that's all divided by the concentration of the undissociated acid, also raised to the power 1. We get those stoichiometric coefficients directly from our reaction. Notice we don't include water because we never include liquids or solids in our equilibrium constant expression. Now, Ka, the smaller the Ka value, the weaker the acid, meaning the less it dissociates in water. Now, for weak bases, the idea is similar. If we call our base B and it reacts with water, it's going to produce hydroxide ions and the conjugate acid Hb with a +1 charge. Again, only a fraction of the base molecules participate, and the rest remain unionized. We define the base dissociation constant Kb as the concentration of the conjugate acid raised to the power 1 times the concentration of hydroxide, also raised to the power 1, divided by the concentration of the unreacted base, also to the power 1. We get those values from our stoichiometric coefficients directly from our reaction. And just like before, a smaller Kb means a weaker base because less dissociation occurs. Now that we've introduced Ka and Kb, the next big question is, how are they related? Remember, acids and bases, they're linked through their conjugates. So Ka and Kb are not independent of each other. Let's work through an example and see why. Let's take the bicarbonate ion, HCO3 with a -1 charge. If bicarbonate acts as an acid, it can donate a proton to water, and that reaction produces carbonate, which is written as CO3 with a 2- charge, along with hydronium. The equilibrium constant for that reaction is Ka, where Ka equals the concentration of carbonate times the concentration of hydronium divided by the concentration of bicarbonate. But bicarbonate, it can also act as a base. So in that case, it accepts a proton from water. The result is that bicarbonate turns back into carbonic acid, written as H2CO3, and it produces hydroxide ions as well. The equilibrium constant for that process is Kb, which equals the concentration of carbonic acid times the concentration of hydroxide, and that's all divided by the concentration of carbonate. Now, here's the clever step. If we take those two reversible reactions and we add them together, most of the species cancel out. And what's left is simply two water molecules in equilibrium with hydronium and hydroxide. And that should look very familiar because it is the autoionization of water. The equilibrium constant for that process is Kw, which is the water dissociation constant. And because we arrived at it by combining the acid dissociation and the base dissociation reactions, it follows that Ka multiplied by Kb equals Kw. And at room temperature, which is 25 degrees Celsius, Kw is 1.0 times 10 to the negative 14. So the key relationship is this. Ka times Kb equals Kw. That means if you know Ka for a conjugate acid, you can immediately calculate Kb for its conjugate base and vice versa. And this link is extremely useful, and it's going to guide us as we move into more calculations involving weak acids and weak bases. At this point in our lecture, I want to step back and make a few things clear. Some of this is going to be review, and some of it will introduce some new relationships. So first, the character of an aqueous solution, whether it's acidic, basic, or neutral, that comes down to the relative amounts of hydronium and hydroxide. If the concentration of hydronium ions is greater than the concentration of hydroxide ions, then the solution is acidic. If the concentration of hydronium ions is less than the concentration of hydroxide, then the solution is basic. And if the two concentrations are equal, then the solution is neutral. Because these concentrations are often very small numbers, we use the log P scale to make it easier to work with. By definition, pH is going to be the negative base 10 log of the hydronium or hydrogen concentration. Likewise, pOH is the negative log of the hydroxide concentration. So we can write pH equals negative log hydrogen ion concentration, and we can write pOH equals negative log hydroxide ion concentration. These two scales, they're tied together by water's autoionization. So the equilibrium constant for that process, Kw, is equal to the concentration of hydronium multiplied by the concentration of hydroxide. At 25 degrees Celsius, Kw has the value 10 to the negative 14. Taking the negative logs of both sides gives us the important relationship that pKw equals pH plus pOH, which equals 14. That means if you know either the pH or the pOH, you can then immediately calculate the other just by subtraction. So for example, if the pH is 3, then the pOH must be 14 minus 3, and that is equal to 11. Because hydronium is much larger than hydroxide in that case, you can say that the solution is acidic. And here it's going to be important to remember that the relationship pH plus pOH equals 14, that holds specifically at 25 degrees Celsius, since that's where pKw is 14. Now, let's place weak acids and bases on an analogous log scale. So for a weak acid, the acid dissociation constant Ka measures how much the acid donates protons at equilibrium. We define pKa as the negative log of Ka. Because taking a log inverts the scale, a smaller Ka corresponds to a larger pKa. And that's why we can say smaller Ka means weaker acid, and equivalently larger pKa means weaker acid. For a weak base, the base dissociation constant, Kb, measures how much the base accepts protons or produces hydroxide at equilibrium. We can define pKb as the negative log of Kb. So, smaller Kb or larger pKb means a weaker base. Conjugate acids and bases are linked through water's autoionization, so their equilibrium constants are also linked. Ka multiplied by Kb equals Kw, which is the water dissociation constant. Taking negative logs of both sides gives the relationship pKa plus pKb equals pKw. At room temperature, pKw is 14, so pKa plus pKb must equal 14 for any conjugate acid-base pair. And this relationship also means that stronger the acid, the weaker the conjugate base. And the stronger the base, the weaker its conjugate acid. So using these equations, once you know Ka or pKa for a weak acid, you can then immediately determine Kb or pKb for its conjugate base, and of course, vice versa. So to summarize, compare hydronium and hydroxide to decide whether your solution is acidic, basic, or neutral. Use pH and pOH to report those concentrations on a convenient scale. And for weak species, use Ka, Kb, pKa, and pKb to quantify how strongly they donate or accept protons. Let's now go ahead and tackle some practice problems together. The first problem says that Kb for ammonia is 10 to the negative 4. What is the pKa for its conjugate acid? Ammonia is NH3. So the conjugate acid of ammonia, when it gains a proton, is going to be ammonium, NH4, with a +1 charge. Since conjugate pairs are linked through water, Ka for ammonium and Kb for ammonia are related by the equation Ka times Kb equals Kw. At room temperature, Kw is 10 to the negative 14, which on the P scale is pKw equals 14. It's faster to work on the P scale, so that's what we're going to do here. pKb is the negative log of Kb, so pKb equals negative log of 10 to the negative 4, which is 4. For a conjugate pair, pKa plus pKb equals pKw. So rearranging that equation to solve for pKa, we get that pKa equals 14 minus pKb. That gives us 14 minus 4, which is equal to 10, and 10 is our pKa. So the correct answer for this problem is A. The second problem asks, these acids are listed in order of decreasing strength. We have hydrochloric acid, hydronium, and hydrogen cyanide. List their conjugate bases in order of decreasing base strength. The move here to solve this problem appropriately is to flip the acid strength order when we switch to their conjugate bases, because the stronger the acid, the weaker its conjugate base. So first we're going to write out the conjugate bases. For hydrochloric acid, HCl, its conjugate base is the chloride ion. For hydronium, its conjugate base is water. For hydrogen cyanide, its conjugate base is the cyanide ion. Now we're going to rank base strength from strongest to weakest. The weakest acid on the list is hydrogen cyanide, so its conjugate base, the cyanide ion, is going to be the strongest base. Next comes hydronium, whose conjugate base, water, is weaker than cyanide ion, but stronger than the chloride ion. Finally, hydrochloric acid is the strongest acid, so its conjugate base, the chloride ion, that is going to be the weakest base. So putting that in order, from strongest to weakest base gives us cyanide ion, water, and then the chloride ion. And that matches answer choice D. We are now ready to move into our next discussion. In general chemistry, we're going to encounter many different acid-base reactions. For this lecture, we're going to start with the most simple case, a weak acid in water or a weak base in water. What we will see is that we can write two equations, one that allows us to solve for the hydronium concentration of weak acids in water, and another that's going to allow us to solve for the hydroxide concentration of weak bases in water. I'll show you how these equations come from Rice tables so that you understand their origin. But you'll also see that you can often just use these equations directly for these types of problems. The first step in solving these problems is always to identify what you're dealing with. Are you starting with a weak acid or are you starting with a weak base? Once that's clear, you can set up the appropriate equilibrium expression. Let's take a weak acid first. We're going to call our weak acid HA. In water, HA reacts with the water to produce hydronium ions and the conjugate base, which we write as A with a -1 charge. At equilibrium, the constant that governs this process is Ka, which is the acid dissociation constant. Ka equals the concentration of hydronium ions multiplied by the concentration of the conjugate base, and that is divided by the concentration of undissociated acid. Now, how do we actually calculate those concentrations? This is where the Rice table comes in. Rice stands for reaction, initial, change, and equilibrium. We begin with writing our reaction, and once that's done, we can think about the initial acid concentration. Let's call it C sub A. At the start, there's no hydronium or conjugate base present. But of course, as the reaction proceeds, some amount of X of the weak acid dissociates, and then it produces X hydronium ions and X conjugate base ions. At equilibrium, the hydronium concentration is X, and the conjugate base concentration is also X. And the remaining weak acid concentration is going to be C sub A minus X. So then we can take those values and substitute them into the Ka expression. That gives us Ka equals X squared over C sub A minus X. For most weak acids, the amount that dissociates is very, very small compared to the initial concentration. And that allows us to make the common approximation that C sub A minus X is roughly equal to C sub A. And with that simplification, the math becomes so much easier. Ka equals X squared over C sub A, which rearranges to X equals the square root of Ka times C sub A. Remember that X here is the hydronium concentration, so we can write a useful shortcut. For a weak acid in water, the hydronium concentration equals the square root of Ka times the initial acid concentration. And from there, pH is simply the negative log of that hydronium concentration. We can apply the exact same logic to a weak base in water. Let's call our base B. The reaction is B plus water produces hydroxide ions and the conjugate acid HB with a +1 charge. The equilibrium constant for this process is Kb, which is the base dissociation constant. Kb equals the concentration of hydroxide multiplied by the concentration of the conjugate acid divided by the concentration of unreacted base. Again, we can turn to our Rice table. We write out the reaction at the very top, and then we're concerned with initial concentrations. We start with an initial concentration of our base. We're going to denote that as C sub B. At the start, there is no hydroxide or conjugate acid present. But of course, as the reaction proceeds, some amount of X of the weak base reacts, and it forms X hydroxide ions and X conjugate acid. At equilibrium, the hydroxide concentration is X, the conjugate acid concentration is X, and the remaining concentration of base B is C sub B minus X. We're going to take those values, we're going to substitute them into the Kb expression. That gives us Kb equals X squared over C sub B minus X. And just like before, if the base is weak, then X is small compared to C sub B. So we approximate C sub B minus X as simply C sub B. That reduces the equation to Kb equals X squared over C sub B, and we can rearrange that to solve for X. X equals the square root of Kb times C sub B. Since X is the hydroxide concentration, our shortcut is, well, for a weak base in water, the hydroxide concentration equals the square root of Kb times the initial base concentration. And once we have the hydroxide concentration, we can calculate pOH as the negative log of our hydroxide concentration, and then use the relationship pH plus pOH equals 14 to determine the pH. So to summarize this section, weak acids in water and weak bases in water require equilibrium calculations, but with our approximations, we can simplify the math into two very useful equations. For weak acids in water, the hydronium concentration equals the square root of Ka times the acid concentration. For weak bases in water, the hydroxide concentration equals the square root of Kb times the base concentration. Let's now tackle a practice problem. The question asks, what is the pH of a 10 to the negative 3 molar solution of formic acid if Ka equals 10 to the negative 4? Formic acid is not on the strong acid list, so we treat it as a weak acid, which is written as HA in our generic setup. For a weak acid in water, our shortcut from the Rice table says that the hydronium concentration, or the hydrogen ion concentration, equals the square root of Ka times the initial acid concentration. Here, Ka is 10 to the negative 4, and the initial concentration, C sub A, is 10 to the negative 3. So the product inside the square root is 10 to the negative 7. The square root of 10 to the negative 7 is 10 to the negative 3.5. So that means the hydronium or hydrogen ion concentration equals 10 to the negative 3.5. We can then go ahead and calculate the pH because pH is the negative log of that number. The negative log of 10 to the negative 3.5 is 3.5. So the pH is 3.5, and the correct answer here is B. With that, we're ready to move into our next topic, which is about simple buffers. So first, let's ask, what exactly is a buffer, and why do we care about them? A buffer is a solution that can resist changes in pH when small amounts of acid or base are added. Buffers are incredibly important. They're everywhere in chemistry and biology. For example, blood is buffered at a pH around 7.4, and if that buffer system stopped working, even small chemical changes in the body would cause huge problems. So, what makes a buffer different from the weak acid and weak base examples we just finished? In those cases, we just had one species present, either a weak acid by itself in water or a weak base by itself in water. And that system, it will reach equilibrium, but it's not going to have the extra capacity to neutralize any additional acid or base that could get introduced. A buffer, on the other hand, always contains both members of a conjugate pair in solution, either a weak acid together with its conjugate base, or a weak base together with its conjugate acid. And having both present at the same time is what makes the solution special. It creates this built-in reservoir of both the proton donor and the proton acceptor. And that reservoir is what allows the solution to absorb stress and keep the pH from shifting too much when you add in a little extra acid or base. Now let's begin with discussing an acidic buffer. A classic example is acetic acid mixed with sodium acetate. The weak acid, acetic acid, it can donate protons in equilibrium, while the salt provides a large supply of acetate ions, which is the conjugate base. That reservoir of conjugate base is key because if you add a little extra hydronium ion to the solution, the acetate ions are going to react with it and soak it up, and it will minimize the pH change that happens. Mathematically, we can describe this with the equilibrium expression. For the weak acid, Ka equals the concentration of hydronium ions times the concentration of the conjugate base divided by the concentration of the acid. Rearranging gives us an expression for the hydronium concentration in the buffer solution. Hydronium equals Ka multiplied by the ratio of acid concentration to base concentration. So the concentration of hydrogen ions equals Ka times C sub A over C sub B, where C sub A is the concentration of the weak acid and C sub B is the concentration of the conjugate base. If you take the negative log of each side, you get the pH is equal to pKa plus the log of your conjugate base concentration divided by your acid concentration. This is called the Henderson-Hasselbalch equation. Now let's look at a basic buffer. A good example is ammonia together with ammonium chloride. The weak base ammonia can accept protons and produce hydroxide ions, while the salt provides a reservoir of ammonium ions, which is the conjugate acid. Here, the presence of ammonium ions is really important because if extra hydroxide is introduced, ammonium ions can react with it and prevent the pH from shifting too high. The equilibrium constant we use here is Kb. Kb equals the concentration of hydroxide ions times the concentration of the conjugate acid divided by the concentration of the base. And rearranging this gives us an expression for hydroxide concentration in the buffer. Hydroxide concentration equals Kb multiplied by the ratio of base concentration to acid concentration. So we can write concentration of hydroxide ions equals Kb times C sub B over C sub A, where C sub B is the concentration of the weak base and C sub A is the concentration of the conjugate acid. And if you take the negative log of each side, you get that POH is equal to PKB plus the log of your conjugate acid concentration divided by your base concentration. This is also the Henderson-Hasselbalch equation, but for POH as opposed to pH. With that information in mind, let's go ahead and tackle two practice problems together. The first problem asks, what is the pH if 1 mole of formic acid, HCOOH, and 2 moles of sodium formate, NaHCOO, are placed in 1 liter of water? The Ka value for formic acid is 2 times 10 to the negative 5. Before we calculate anything, we should identify the situation. There are 2 species that are present here, and they are a conjugate pair. We have formic acid, which is a weak acid, and we have sodium formate, which supplies its conjugate base, formate, HCOO with a negative 1 charge. So having both HA and A with a minus 1 charge, these are our general forms for a weak acid and its conjugate base, having those in the same solution is the hallmark of a buffer. So we use the weak acid buffer relation. Hydronium concentration equals Ka multiplied by the ratio of acid concentration to base concentration. So that equals Ka times C sub A over C sub B. Because the total volume is 1 liter, the molar amounts are also the molarities. So C sub A equals 1 molar and C sub B equals 2 molar. Substituting that into our equation gives us that the hydrogen ion concentration equals 2 times 10 to the negative 5 multiplied by 1 over 2, which is 1 times 10 to the negative 5. Converting to pH, the negative log of 10 to the negative 5 is 5. So the pH is 5, and the correct answer for this problem is B. The second problem asks, what is the pH of a 0.1 molar solution of methyl ammonium bromide if the ratio of ammonia to ammonium is 4.0, the ammonia concentration is 3.2 times 10 to the negative 3 molar, and the Kb for ammonia is 10 to the negative 5. I'm going to start by spotting the pattern. Ammonia is a weak base, and ammonium is its conjugate acid. And because both members of the pair are present, this is a basic buffer. For a basic buffer, the hydroxide concentration equals Kb multiplied by the ratio of base to conjugate acid. So we can write that the hydroxide ion concentration equals Kb times C sub B over C sub A. Now I can plug in the numbers. The problem gives the base concentration directly. It is equal to 3.2 times 10 to the negative 3 molar. Then it tells us that the ratio of ammonia to ammonium is 4:1. So the concentration of ammonium must be 1/4 of 3.2 times 10 to the negative 3, which is 8.0 times 10 to the negative 4 molar. Now, using the buffer relationship, the hydroxide ion concentration equals 1.0 times 10 to the negative 5 multiplied by the fraction 3.2 times 10 to the negative 3 over 8.0 times 10 to the negative 4. That fraction is exactly equal to 4. So the hydroxide ion concentration equals 4.0 times 10 to the negative 5 molar. Next, I convert to POH. I take the negative base 10 log of 4.0 times 10 to the negative 5. So POH equals minus log of 4.0 minus log of 10 to the negative 5. That is 5 minus the log of 4.0. The log of 4.0 is about 0.602. So POH is approximately 5 minus 0.602, which is 4.398. Let's call it 4.40. Finally, I use pH plus POH equals 14 at 25 degrees Celsius. So pH equals 14.00 minus 4.40, which gives us 9.60. So the correct answer for this problem is D. And with that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. In the next video, we're going to talk about titrations. Other than that, good luck, happy studying, and have a beautiful, beautiful day.